Last month, we were fortunate to have microbiologist and colloidal chemistry expert Dr. Robin Wakeling present his analysis of Pfizer Comirnaty under the microscope. Since that time, Dr. Wakeling has continued to investigate the injection and has also linked up with other New Zealand teams who have shared their findings with him. In part one of his analysis, Dr. Wakeling presented the appearances of Comirnaty straight from the vial and has some new information regarding how these complexes form. But perhaps more importantly in this video, for the first time, he is going to analyse the blood of some Pfizer injected subjects who have suffered adverse reactions. He'll explain what he thinks is happening to their red blood cells and some of the most bizarre images he has ever seen in his long career. In addition to Comirnaty, the teams have also been investigating recent influenza vaccines under the microscope, with some surprising findings that the officially disclosed ingredient lists don't appear to explain. Dr. Wakeling joins my husband, Dr. Mark Bailey, to present round two of Pfizer under the microscope.
Welcome everybody. This is Dr. Mark Bailey. I'm joined again by Dr. Robin Wakeling coming in from Wellington, New Zealand. Robin presented his findings of Pfizer Comirnaty under the microscope on the 22nd of March this year. And if you haven't seen that video, it would be a good idea to watch that one first, because tonight is a follow-up video. Robin's been doing further analysis of the Pfizer product under the microscope, including linking up with some of the other New Zealand teams who have been investigating the injection under the microscope as well. So Robin's also been in touch with various scientists around the world who have provided some interesting feedback here and there. Without further ado, I'll let Robin explain some of his latest findings.
You've got a slightly new title here, Light Microscope Evidence for Liquid Crystal Structures from Vaccines and Red Blood Cells, and I'll explain how those two tie together as we go through. I'm going to start by talking about the light microscopy of the Comirnaty, so Comirnaty Part 2. We've also been making some very similar observations with regards to some of these unusual structures that are developing in vitro from another vaccine, the Al-Fluria Quad Flu Shot. I've been working with another doctor to start to consider some of the effects of vaccine on blood, in a very tentative way. So this is blood from people who have been vaccinated. Here we have it's basically a rectangle, 4 sides, very straight edges. That's about 100,000 nanometers, so 100 micrometers. That's about as simple as they get. Larger structures like this, although this is by no means the largest. Occasionally, some of the smaller ones will form in the free floating phase between the 2 layers of glass. They seem to need an interface to form these more complex structures. You know, we've got a very long, thin structure here attached to it almost looks like a walkie-talkie with a sort of a body, wider sheet-like bit here. But it's part of the same structure, and you can see these forming in real time. It's quite unusual. I mean, that if you look really hard in some of the literature, you can find references to similar things. I mean, there has been a lot of interest in the last 10 years in two-dimensional crystals, particularly forming from liquid crystals. But it's still fairly rarefied, even though there's been a sort of an explosion of interest in the last 10 years. And I haven't managed to find anything quite as weird as some of these structures, certainly not the variety. So this is just a classic shape, standalone shape. The reason this is fuzzy is because it's so big. You've got a nice clean area within the structure and then this very clean edge, and it's pushing aside everything else on the glass as it's forming. That's very characteristic. There are exceptions that I'll talk about, but that's the basic form. And this is a much larger one. There's another one in the corner here. You can see these are quite fragile. If you slide the cover slip around, you can start to break them up. So they are fairly soft, but once they get to this size, they seem to set, and it appears that they don't sort of dissolve and then come back again. If you mess these up, or if you break these up, they just break up into a lot of amorphous granular particles. They don't appear to reform. Here's one here where you can start to see another layer. So if you look, so here's the base layer here, and then there's a layer of the actual community sort of sitting on top in little globules, and in places it's starting to form another straight edge structure on top of the first layer. You can just see it there. This is one of the previous ones I showed from the previous presentation, and you can actually see the different layers here. So there's a single structure on top of this much larger structure here, and then you've got lots of individual structures here. So this is mainly two layers. There's a base layer, and then there's a second layer of structures. Whereas this one here was older. I've had this for at least 2 weeks now, and it didn't change. So it was a single layer. Sometimes it's quite hard to see whether you're dealing with another layer on top or whether this is just adjacent bulk phase liquid. This is actually not community. This is our Fluria quad flu shot. We found that this particular vaccine produces these structures even more readily than communities, or much more consistently. The triggers don't seem to be as hard to predict, but it pretty much does this every single time. I haven't had any trouble producing these structures from this particular vaccine, irrespective of how it's handled.
Which year is the flu vaccine from?
This is 2021, but the same thing happens with 2022. The only one that I haven't yet had it happen with, it was a 2022 one, but it was specifically labeled for 65 years of age over, and I have no idea why that would be. But it had a different consistency. It was a slightly milky color, whereas all the other Afluria quad preparations were completely clear. When the emulsion starts to get slightly milky, it usually means that the individual micelles or lipid nanoparticles or liposomes or whatever's being used to formulate the key components of the vaccine, they're larger. So this is dark field, and this is firstly to show you just how expansive these are. These are all, sometimes you can follow these for several centimeters. They're huge. And it's, I guess sometimes they must merge, but there is a suggestion that they seem to avoid each other once they get close to each other. Now, these structures, particularly in the Afluria quad, they seem to occur often at the margins of the retreating front of the liquid phase. So as you leave these, they gradually dry out. And these structures very often form, you can see at this boundary here. That's quite common. It's not exclusive. Sometimes they also form along the cover slip edge, the drying zone. Sometimes components within the formulation there's a phase separation. This is not unusual because when you form an emulsion, you've got all kinds of different aliphatic molecules, lipids, solvents, co-solvents, buffers, all kinds of things in there, and sometimes they separate. One will be a more aqueous phase and one will be a more hydrophobic phase, and sometimes these crystals will form at that interface. So it doesn't have to be an air-liquid interface, it can be just two different liquid phases. Now, I've just got a series of images here. These are still shots to help you get a feel for the scale or the size of these things. Field of view here is 600 microns from top to bottom, and then across from right to left, about just over 1,000 microns, so about a millimeter. So that gives you a feel for the size. If we go to the next one, it's the same thing, but magnified. So it's twice the size. Part of the reason for doing that is just to see if we can see anything at higher magnification, but it's also to illustrate that these edges, in most cases, are still very straight. One of the strengths of dark field is it's very good at showing edges where interfaces meet. It's pretty hopeless at showing you what's in the middle of a structure. That's where phase contrast or bright field is better. But it really is excellent at showing contrast at edges or interfaces. There it is, twice the size again. So it's a fourfold increase in scale there. And we've still got fairly straight edges. There's a slight hint here that hasn't fully formed into a straight edge, or maybe it was damaged, but usually straight edges, some kinks. We can watch these forming in real time. This was after about 20-25 minutes from putting the community on the microscope slide, putting a cover slip on it, and then putting it under the phase contrast, looking at it immediately. And the structures are starting to form, but this is quite fast. So this is about a micrometer a minute. Things do slow down later. That tends to only happen for the first hour or slightly less. And then in other cases, it's completely different. Some of these things that look like they're merging, they're actually not. Some of them are on the underside of the cover slip, and some of them are on the top face of the microscope slide. So they're not actually touching. They do seem to have an aversion to each other, especially these ones that I watched. I literally sat there for 90 minutes and watched these things grow. I never actually saw one where I could put my hand on my heart and say that definitely merged and became one and the same thing. I think it must happen, but there is a suggestion that they're discrete little colonies, if you like. This is somewhat different in as much as the time frame was similar, but you can see the formations are slightly different. These are basically just like miniature versions of those much larger ones. So this is the same scale. It's the same magnification as those phase contrast images I was showing you before. They're just smaller versions. This is Comirnaty again. Now, we've noticed that there's quite a powerful surface tension effect. In the previous talk, I'd almost convinced myself that a magnet was affecting movement of some of these particles. Well, it turned out that it wasn't the magnet as such. It was simply the weight of the magnet was causing a greater surface tension. Once the liquid layer reaches a critical depth, the surface tension makes it extremely hard to pull them apart. Surface tension is very powerful. It seems that when you put a very thin layer of Comirnaty between the cover slip and the microscope slide, so it's just enough to completely cover the interface, basic physics will tell you that you'll have a higher surface tension than if you put a much larger droplet, maybe 5 to 10 times the volume, and then you just drop the cover slip on. It's almost floating. Early on, if you have a higher surface tension caused by a much shallower depth of liquid, different things happen. These shapes often don't form at all, or they take much longer to form. The other difference is that we get these odd patterns where these little particles are actually moving around and leaving an imprint of themselves. And sometimes you can actually see them doing it in real time. So there's definitely some movement there. You can actually see it happening sometimes. This is also Comirnaty. Now, sometimes we look for these structures, maybe for half a day, and we just don't see them. Nothing happens. But sometimes things happen within the first hour quite consistently. And other times you have to leave them for somewhere between 12 and 18 hours. I know we've probably looked at about somewhere between 50 and 100 slides now. And I would say about a third of them, nothing ever happens ever. No, they just dry out and we don't see any of these structures. Another approximately a third form the smaller structures quite quickly and you can watch them forming in real time. And then the other third, you can't see anything in real time and you can track or you can look for development over a whole working day, and then nothing happens, and then you come in the morning and hey presto, there'll be these nice big structures. And over here you can see a liquid layer on top. Sometimes this seems to be associated with the deposition of another layer on top. Sometimes it could be just because the liquid is sort of swamped over the top after it's formed, and sometimes it's like it's actually forming out of the liquid. I quite like this one because you can get the impression that this one has formed within the bulk phase itself, or it might have started to form at this interface. But over here, it seems to be forming and pushing apart the bulk phase. So this is the actual Comirnaty bulk phase here, and it's pushing it aside. It takes on a slightly different color once it forms these soft, solid structures. And this is another layer on top. So we've got a double, we've got two layers. So it's sort of starting to form a more three-dimensional structure. And sometimes the second, that little antenna there is very, very thin. So some of these things are quite delicate. These are crystals of cholesterol. You can see that there's several layers of these planar sheet-like crystals. Cholesterol is a very interesting fat. It's found all over the body. I mean, we couldn't function without it. It's absolutely vital to cell biology. For example, 50% of the plasma membrane of red blood cells is cholesterol. Sometimes we also see it in urine. It's very common in damaged tissue. You get deposits of cholesterol. So I looked at all the ingredients in those two vaccines and tried to think, well, is there any evidence in the literature that they form crystals that might look like this? And this was the closest match I could find, except that as far as we know, there's no cholesterol in Afluria quad. There is cholesterol in Comirnaty, it's listed, and yet we're seeing identical structures in both of these vaccines, which is something of an anomaly, which we don't have an answer for, other than that there might be something in both these vaccines that are causing these structures to form. Sometimes something can look like a cholesterol, not because it is cholesterol, but because of this wider phenomena called cholesteric ordering. Cholesteric ordering is a very important phenomena in biology. Comirnaty and Afluria quad may contain a liquid crystal that exhibits cholesteric ordering. In fact, I think it's extremely likely. And that is a widespread phenomenon that affects many liquid crystals and which defines potentially important functionality. So red blood cell membranes are known to unravel into free colloidal structures in response to stress. For example, poisons. Certain lipases will do this. Cells are very robust. They're very good at repairing themselves. They're very good at resisting things as long as they're not something that's just come totally out of left field that they have never encountered before. It did appear that red blood cells from Comirnaty injected people disintegrated much faster and more comprehensively. Now, if you take red blood cells out of any person, very healthy people or less healthy people or people in between, over a period of many days, you can just start to see this starting to happen, but it's very subtle and quite difficult to find. You might need to look at several hundred red blood cells before you find one doing this. Whereas blood from people who had an adverse reaction after having the Comirnaty injection exhibited these effects far more readily. This is just a reminder of what red blood cells should look like under dark field. Nice spherical structures. These are about 7 to 8 microns across. So they're sort of spherical in one plane, and then they have a sort of a bagel shape on the top and bottom plane. This is blood that was taken from someone who had been injected, and then images were taken somewhere between half an hour and an hour after being put on the microscope slide. You can see there's a nice curve to the outside of the red blood cell. That is actually a red blood cell, it's not a water bubble. And then sometimes they start to deform like this. It starts to look more like an amoeba than a red blood cell. And then sometimes they completely unravel, and you can see these membranes here, or they're not membranes anymore, they're just long colloidal rods. They're starting to show this property of cholesteric ordering, where they're wrapping around each other in this helical fashion, which is a classic occurrence for a colloidal material like this, or liquid crystal. So there you can see things moving around. They're moving around for the same reason that the colloids were moving around in vitro for the colloidal structures that were present in the Comirnaty. So similar thing happening here for similar reasons. So these are colloidal structures that are forming from breakdown of the plasma membrane. These still seem to be attached to what used to be a red blood cell. These little things here are probably lipid droplets, but they're starting to look pretty weird. And if you look through to this, some people mistakenly identify some of these things as parasites. They're not parasites, they are liquid crystal colloidal structures. These things don't start to disintegrate immediately, or this unraveling of the plasma membrane, it doesn't happen immediately. And sometimes you need to stress them slightly, like a little tap on the cover slip. But if you do the same thing to a healthy blood cell, they're quite robust. They don't behave like this. I mean, I've been messing around with my own blood. I might have approached 1% of this effect, nothing like this at all, really. This is a really extreme form of this unraveling. I haven't managed to find anything in the literature that's comparable to this. It's just fascinating. You can just to look at these, you can see there's a rod shape there. That's almost identical to some of the rods that we were seeing forming from Comirnaty in vitro. And that's most likely because they're formed of similar colloidal materials, liquid crystal materials. It almost looks like some kind of sea life. but I can assure you it's not. It's a colloidal structure that's forming from breakdown of the red blood cell plasma membrane. But if you didn't know what you were looking at, you could be forgiven for thinking that was something a bit more scary than that. Although having red blood cells disintegrate like that quickly is pretty scary in its own right. We don't really need to start looking for parasites and microorganisms to explain it. It's a poisoning effect, most likely. So these are just variations of the same thing. I like this one because it's showing the cholesteric ordering effect. So we've got this helical effect occurring. It's quite clear there. Almost looks like a string of DNA, but of course it's not. It's just aliphatic colloidal liquid crystal molecules exhibiting cholesteric ordering. So they're forming a helix like that, wrapping around each other. So that's a single rod that's just wrapped around itself in a helix, like a little noodle, spaghetti noodle. Here you can actually see an original blood cell. It's sort of just started to collapse, and the center is filled up with all these little lipid particles from the bulk phase. And in fact, I understand the doctor that took these images, actually, they were so confused at what they were looking at. They shared this with one of the country's leading blood experts, and they had no clue what was going on. It's only because of my knowledge of colloidal chemistry that it was pretty obvious to me what was going on. But you can find this in the literature if you look hard enough. Not quite as spectacularly as this, but in other contexts, there are references in the literature to red blood cell plasma membranes starting to behave like this. But this is a very extreme form of it.
And Robin, do you know if the patients the doctor took the blood from here, were they unwell or did they just want the blood checked?
Well, these images were taken from two people. One had a history of being not particularly well, but the consultation was because of an adverse reaction, or so they thought. The other patient was I understand, a very fit, athletic 30-year-old who was apparently in excellent health, but then they had an adverse reaction. So some of the other images that I'm going to show you were from, I think 2 of them were from that person. So very similar effects, which is a bit of a concern. Here's another one. This is the one that looks a bit like a sea star. A sea star is a marine creature, same family as starfish, but it's just a complex colloidal structure that's formed from breakdown of the red blood cell plasma membranes. So this looks a bit like a cookie cutter, but it's the remains of the red blood cell plasma membrane. The center of the cell is basically gone, and that's just probably lipid particles from the bulk phase that has accumulated in there, got trapped inside for some reason. Or some of the plasma membrane may have defibrillated and sloughed away into the sort of cytosolic space, or what was the cytosolic space. So that might be partly what's happening there. Whereas this one is, I don't think that's an original blood cell. I think that's just one of these rod-shaped colloidal structures that's formed from the plasma membrane. It's just wrapped around on itself. The plasma membrane sloughed off the red blood cells, and then it's wrapped around on itself. But some of the red blood cells did, or what appeared to be red blood cells, seem to take on this form here. So I think that one probably was originally a red blood cell. But because they break down so badly, it's quite hard to tell sometimes. But clearly there's something quite different there. These are colloidal structures, and they're moving because of the repulsive and attractive forces between the aliphatic molecules within the structure and the aqueous bulk phase surrounding it. So this blood, I think, was in standard saline preparation. So it would have been presumably chosen to be isotonic with the cytosol of the red blood cells or something close to that. So this breakdown is not because of some hypertonic effect. And that's certainly not what you get with putting red blood cells in either a hypertonic or hypotonic solution. They don't behave like that. But, they will deform or explode. It's a bit grainy because this was taken on someone's camera phone. But, for someone who looks at blood every day, to look at that and think, I don't know what's going on there, seems to be quite significant. I'm not a blood expert, but I was only able to work out what's going on here because of my other fields of expertise in colloidal chemistry, and that in relation to biology. I guess if you're an expert in blood, just because this is such a extreme version of what you might see from time to time. You wouldn't necessarily realize what it was. But they're certainly quite fascinating. So this is a more recent working hypothesis. It appears that a substance in Comirnaty and Alfileria cod forms two-dimensional and one-dimensional soft solid structures of a somewhat rarefied form and of an unknown function. Is it an incidental byproduct? Well, it's possible, but we certainly shouldn't leave it at that. I think it would be a big mistake to assume that. Is it coincidence that graphene oxide is known to behave similarly to some of these effects that we're seeing, at least, with the first series of images we were looking at? As I said and went into more detail in the first talk, graphene oxide is known to produce some of these effects, to form sheets, to form liquid crystals, to form these semi-soft two-dimensional and one-dimensional structures, the property of self-assembly, cholesteric ordering, some of the interactions with plasma membranes, it's in the published literature. There's certainly some circumstantial evidence that something in these two injections is behaving in a way which behaves similarly to how you would expect graphene oxide to behave. I think we need much more citizen research. I no longer personally have any faith in the establishment to ask these questions. I've seen people present evidence to MPs, governments, agencies, CDC, the FDA, to the various levels of the court with absolutely no effect. It's just not looked at seriously. So I think, we need much more citizen research, robust debate, and due diligence is needed before we reach conclusions or make any decisions. I'm simply presenting observations and asking questions, and I'm wanting other people to look at this and think, okay, how can I do this better? What's Robin got wrong? What's he got right? How can I improve on that? We mustn't reach premature conclusions or make decisions prematurely. And on that note, that includes taking part in so-called safe and effective experimental injection trials, which is exactly what a lot of people have done. They don't seem to realize that. So yeah, this is in the spirit of sharing. So please share and please fill in the gaps, do more. I'm one of thousands of people doing this sort of thing, and it's starting to grow, which is quite exciting.
Robin, thank you once again for a fantastic presentation. And I'd encourage all our audience, if you haven't seen Dr. Wakeling's first presentation that went public on March the 22nd this year, then definitely watch that, because there's a deep dive into what happens with the Pfizer product under the microscope, comparisons to other vaccines, and a dive into the colloidal chemistry. Tonight was really good, Robin. I think there's a lot of new information there, particularly with regard to seeing the potential effects of the shots in living blood, which was really interesting. Thank you very much. And I guess you may have an update for us at some stage in the future.
Yeah, thanks, Mark. Yeah, I think the flu shot was a bit of a revelation to see exactly the same thing happening in the flu shot. So I guess we need to look at other vaccines too.
Absolutely. So keep up the great work, and thank you once again.
Thanks, Mark.
To help sustain my channel in this time of censorship, please support my work on Subscribestar. Link is in the description. So that we don't lose touch, please find me at drsambailey.com and sign up for my free newsletter.